Welcome back. In this module, we're going to talk about optimizing acquisition for your particular study goals. There's no one best way to obtain fMRI images. There's a sequence of trade-offs among different choices. And many acquisition choices are standardized across an fMRI center or across studies within a center, but others can be customized to fit your particular study goals. The goal of this module is to review acquisition parameters and discuss some of the trade-offs involved so that you can make smart choices for your study when possible. One example of a standard parameter setting or choice is which sequence to use. So echoplanar imaging is the most commonly used. It collects slice-by-slice data from the bottom to the top of the brain. But there are many variants and alternatives for how to do this well, and those relate to how the image space is sampled. So there's also spiral acquisition or volumetric acquisition choices or sequences, how potential artifacts are dealt with. So these include things like spin echo sequences or Z-shimming to reduce artifacts, multi-echo sequences for better neural specificity, and slice-specific echo time and flip angle sequences. They also include other kinds of choices like accelerated data acquisition options. And these include parallel imaging and multiband or simultaneous multi-slice imaging as well. So it might be difficult to have very deep expertise in all the possible techniques and trade-offs if you're not a physicist or engineer working in the area. But you can learn how to talk to a collaborator, a physicist or engineer, and how to make good choices for your study. There are some basic limitations. The first one is time. Whatever sequence you use, there's a limitation in how much data you can collect how fast, and that's a fundamental limitation that governs many of these trade-offs. Secondly, there's a signal-to-noise limitation. fMRI data are inherently noisy. There's thermal noise related to the scanner. There's physiological noise related to head movement, and head movement induced by other kinds of physiological artifacts and other kinds of vascular artifacts as well. Artifacts are endemic in fMRI images. All images have some artifacts. And in fact, the T2 star weighting that produces sensitivity to the Bold effect, the blood flow and oxygenation level dependent effects of interest, are also those that produce susceptibility artifacts, particularly at the boundaries between tissue types, and especially brain and air spaces around the base of the skull. So these vary across participants due to the head geometry, how the sinuses are organized and arranged, and the topography of those spaces, as well as other factors. So they can't be eliminated, but we can choose sequences and parameters in order to be smart about the basic trade-offs. So that's what we get to choose. And there's a space of different points in this series of trade-offs. So on the top of the pyramid here, we have coverage, how much brain you're covering, which trades off with the other parameters, including spatial resolution, temporal resolution, and susceptibility artifacts. So let's look at coverage. That means how much of the brain you acquire, which always takes time. So you can do things to increase the coverage, very simply, acquire more slices. But there are pros and cons to each, listed here in green and red, respectively. So the pros of getting better coverage include better registration of the brains, better normalization or warping across people, so there's better alignment, and of course there's more brain areas to look at that might be of interest. The cons are, in general, you have to go slower. That reduces temporal resolution. It reduces spatial resolution because you have to get bigger voxels if you're acquiring more of the brain. And it increases susceptibility artifacts as well to do those things, to sample more slowly and with bigger voxels. So let's look now at spatial resolution. In spatial resolution, higher spatial resolution gives you sensitivity to more localized signals. And that's determined in part by how small your voxels are, and also by the intrinsic spatial resolution of the scanner and sequence. It's fundamentally limited by the underlying resolution or the point spread function of Bold, which depends in part on the vasculature and the field strength. So some pros of increasing spatial resolution: you can detect activity in smaller brain regions. There's less partial voluming, which refers to averaging over regions that do different things with different populations of neurons or even different tissue types, gray matter and white matter, gray matter and fluid space. In general, you can get better decoding and prediction at 3T with voxel sizes down to about 2 millimeters. And after that, there are additional issues. At 7T, you can go to smaller voxels, and that will likely improve accuracy and decoding in multivariate analyses as well. And finally, there are reduced susceptibility artifacts. A lot of pros. There are costs in signal to noise as you get smaller in voxels and also in temporal resolution. Let's now look at temporal resolution, the third corner of the pyramid. And temporal resolution refers to how slow the signal changes need to be for you to detect them in terms of underlying brain or physiological activity. This is determined in part by the TR, or the volume acquisition time. There's a fundamental limitation here too, which is the slow hemodynamic response, which rises slowly and peaks at about 5 to 6 seconds, as we've seen. However, artifacts can happen much more quickly, related to movement or heartbeats, etc., in the brain, and so there's some value also in sampling quickly to separate out the artifacts from the real signals. So some pros of increasing temporal resolution: we get better sampling of the hemodynamic response function and connectivity, particularly across brain regions. We have better ability to separate out and remove artifacts. There's less aliasing of high-frequency physiological artifacts into the space of the task design or psychological paradigm that you're interested in. And there's lower susceptibility artifacts, primarily because there's reduced head motion during the acquisition of a volume. There's also a large cost, which is the cost in time, in coverage, and in spatial resolution. Now we'll turn to susceptibility artifacts, which are an unwanted consequence of bold imaging. And susceptibility artifacts take two basic forms: signal dropout, or loss of signal, and geometric distortion. And this is particularly true at the boundaries between tissue types, like air and sinuses with brain. Moving structures, like large blood vessels, also produce susceptibility artifacts. And as you can see from the movie here, this ping pong ball, even a spherical shape, when you sample it in the scanner, can often have a distortion. And so that's an example of an artifact. So some pros of sequences that reduce susceptibility include better signal fidelity, better localization, particularly in high susceptibility areas like the orbitofrontal cortex, the amygdala, the ventral temporal cortices. Some cons are reduced sensitivity to the true neurovascular signals of interest, because the signal strength is going down overall, usually. And some procedures can give you a win, but they cost in time, in coverage, or spatial resolution. Z-shimming is an example of that, where there's a benefit in certain slices that are high susceptibility, but there's also a cost because it takes longer to acquire those images. So now let's look at some parameter choices and their effects in this section. So let's review some parameters first. We collect data slice by slice. There's one slice. So one parameter is the number of slices, and also the slice thickness in millimeters. There's the head tilt angle, both of the person in the scanner, but here we're referring to the prescription of the slices, where they're tilted or oriented along the head. That also matters. There's a pre-scan period where certain procedures, like fat saturation that we'll talk about soon, are set up, and shimming is set up to homogenize the magnetic field. And then we collect one volume per TR, as you see here. When we sample one slice, the area that we're sampling in that slice is the field of view, and there's also a grid that's the data are sampled on, and the matrix size refers to how many cubes you divide up that field of view into. So a typical matrix size is 64. For high-res imaging, it can be greater. And the voxel size is determined by the field of view divided by the matrix size, and also by the slice thickness. So 3 by 3 by 3 millimeters would be in terms of the X, Y, and Z directions. And isotropic voxels mean ones that are equal in magnitude across all dimensions. So let's look at some of these parameters. So the TR is the volume time between acquisitions, and a basic recommendation is to keep this under 2 seconds. We found that 1.3 seconds has a good profile for many people in terms of reduced aliasing of cardiac noise. So 1.3 is a value that we like in many of our studies. That also reduces head movement during the image more than a long TR. You can also go much faster in some cases. We'll see that soon. Voxel size is how big the voxels are in the 3 dimensions. And one thing to know is that the signal to noise varies in inverse proportion to the volume of the voxel. So if you have 3 millimeter voxels, that's 27 cubic millimeters, and you compare that to 1 cubic millimeter, 1 by 1 by 1 voxels, that the 1x1x1 has 27 times less basic signal to noise. Now that may be a rate limiting factor if thermal noise is a big issue, or it may not matter too much because it might be dominated by the physiological noise of moving your head and so forth. So generally down to 1 or 2 millimeters is you won't be at the thermal noise threshold usually. But if you really tried to go smaller than that, then thermal noise will become a big issue. One other point is that at 3 Tesla imaging, then the intrinsic smoothness of the bold images are close to 3x3x3 millimeters, perhaps somewhat less, maybe 2.5 millimeters. And so if you go smaller than that, you're really not gaining anything in terms of intrinsic resolution, but you're losing signal to noise. And that's why some studies, like Chemao et al. 2011 is a paper I like, and they found that something close to 3x3x3 millimeters is optimal for decoding at 3T. At 7 Tesla, smaller voxels are going to be helpful. Now let's look at coverage. That's the amount of brain covered. And I recommend whole brain or near whole brain unless you have special reasons to do otherwise. And that's primarily because of the issues with spatial registration and normalization if you acquire a partial volume. Finally, the field of view. And we like to set this is set based on the voxel size that we'd like. So one thing to check for is aliasing or wrapping of the image in space, folding over if the field of view is too small and too tightly coupled around the brain. And there are some ways to deal with that if that happens. Another parameter is the flip angle, and refers to these are parameters that are about how we acquire the images. Flip angle is the amount of magnetization applied to the spins to tip them over into this transverse frame. 90 degrees is a typical value for very long TRs, like 3 seconds or more, but it's TR dependent. There's an angle called the Ernst angle, which is roughly optimal flip angle for a given TR. So a rule of thumb is the Ernst angle minus about 10 degrees. So for a 1.3 second TR, the flip angle would end up being about 70 or so. Echo time is the time from application of the RF pulse in the image to the time that you read out. And the optimal TE depends on the field strength, but it also depends on the local susceptibility artifacts. And the way to think about the trade-off is, if there are high susceptibility artifacts, you want to lose signal in order to also reduce the artifacts. And a shorter TE is going to be better. This is true at the bottom of the brain. At the top of the brain, you have lower susceptibility artifacts, and you can go a little bit longer on the TE and still get really good signal, and then you get more signal strength too. So at 1.5 T, 40 to 50 millisecond TEs are optimal. At 3T, about 22 to 30 milliseconds is a good range. And on the lower end, if you really care more about the bottom of the brain, at the higher end, if you care more about the top of the brain. There are optimized sequences which have slice-specific TE values. The bandwidth is the frequency at which the signal is digitized and sampled. And if you have higher bandwidth, increases acquisition speed at some cost to noise. And this is often set close to the maximum value that the scanner can tolerate, which means that you can get more images faster, higher temporal resolution, at some cost to SNR. Finally, fat saturation refers to a pulse that's often applied before each volume that's acquired, every TR, that essentially saturates the signal in fat with radio frequency energy, and this is recommended because it reduces spatial distortion around the fat-water boundaries at the edges of the brain. So there's some time cost to doing that. And finally, the tilt angle is something very simple that you can control. And this is the angle of the slice prescription from roughly horizontal, let's say, to tilted back. And what we and many other groups like is something that's tilted 10 degrees up from the anterior-posterior commissure line, because that tends to reduce artifacts in the orbitofrontal cortex and the amygdala to some degree. But this is also dependent on the scanner you choose and the sequence as well. Now with two more choices here. And the next one is a parallel imaging factor. So this refers to acceleration of the imaging in a plane within a slice by skipping some portions of k-space and essentially undersampling the image and then going fast. It relies on the use of multiple coils, or also called channels, in the head coil to reconstruct the image and unwrap these things which are aliased and folded on top of each other. There are different names on different platforms. On GE, it would be Grappa, Sense on Philips, or IPAT setting on the Siemens scanners currently. And 1 is no acceleration, or greater than 1 means more acceleration, higher acceleration factor. So some basic recommendations are, some parallel imaging is probably okay and probably necessary if you want whole brain coverage with a TR of 1.3 seconds and 3 millimeter voxels. You'll have to do some parallel imaging. And so that's fine. There's only really a small cost often to SNR and reduced artifacts due to faster imaging. But you should check that on your images. Collect some pilot data. The second basic option is multi-band or simultaneous multi-slice imaging, and this refers to acceleration of the acquisition of a volume by acquiring multiple slices at the same time. So this is a relatively new innovation in 2015. It again relies on the use of multiple coils to unwrap the image. And this is recommended if it's piloted or developed at your center. It can be quite a big win and a great thing, but use it with caution because it's really in development now. So there are benefits related, the same benefits as related to parallel imaging, but greater speed up. So right now we're using a multi-band 8, which is 8 slices at once, which is pretty aggressive. We've done a lot of tests. That's what we recommend for our setup, at least. Combining it with parallel imaging is not recommended because that really increases the artifacts, especially if you're moving your head in the field. So it multiplies the artifacts together. So now here's a summary of these trade-offs that we talked about. And what we're looking at is the trade-off between coverage, spatial resolution, temporal resolution, and susceptibility artifacts. And here what you can see is things that you might want to do on the rows there, and on the columns, choices that you can make. So for example, if you scan at a higher field strength, there are wins in contrast to noise and bold sensitivity, which is what you want at the end of the day, and in spatial resolution. But there are costs in susceptibility artifacts and susceptibility to motion-induced artifacts as well. If you choose a shorter TE for your field strength, then you reduce susceptibility artifacts, and that's good, but it costs you in contrast to noise and bold sensitivity to some degree. If you choose smaller voxels, benefits in spatial resolution and susceptibility artifact resistance, but costs potentially in coverage, in contrast to noise, in bold sensitivity and temporal resolution. If you choose a shorter TR, that's faster imaging, there are gains in temporal resolution, susceptibility artifact reduction, and physiological artifact reduction. And there are costs, again, potentially in brain coverage, in contrast to noise, and in spatial resolution. And finally, if you choose accelerated imaging, you can get a lot of potential benefits. They include increased coverage, given other parameter settings, increased spatial and temporal resolution, increased susceptibility reduction, artifact reduction, and reduced sensitivity to physiological artifacts. But there are costs intrinsically in contrast to noise and bold sensitivity because of the acceleration. So this can help you think through some of the trade-offs for your study. That's the end of this module. Tune in again next time.